Power functions frequently show up in direct proportionality models. Roughly, we can say that two quantities are directly proportional if one is a constant multiple of the other. A more precise way of saying this is that there's a constant value k, so that q is equal to k times r. So to construct such models, suppose we knew that q is directly proportional to the cube of x. And we also know one point of data. We know that if x is 2, then q is supposed to be 32. Can we use this information to express q as a function of x? The first line almost completely specifies the function. It says that it's directly proportional to the cube of x, so q is equal to some constant k times x cubed. All that remains now is to figure out what value of k we should choose. If we substitute in the single point of data we have, we know that when x is 2, q of x is supposed to be 32. So we have 32 is equal to 8 times k, and then dividing both sides by 8 gives us that k is 4. This lets us go back and completely specify the function, that q of x is actually 4 times x cubed. As a direct proportion, q is 4 times as big as the cube of x. Quantities that are directly proportional have the nice property that multiplying the input results in some predictable multiplication of the output. So as an example, what would happen if we doubled x in the function we just built? Let's just plug in a few values and see if there's a pattern. Plugging 1 into 4x cubed would give us an output of 4. If we double x to 2, now the output would be 32. If we double x to 4, the output would be 256. If we double x to 8, the output would be 2048. The table suggests that each time we double x, we multiply q by 8. We can actually confirm this from the definition of the function. If we're wanting to double x, then we're asking what happens to q when the input is twice x. Substituting 2x into the definition would give us this expression, and then distributing the cube gives us a factor of 8. And you'll see that essentially we have q of x hiding in there with a new factor of 8. So I can switch the order of multiplication just to make it look more like q of x. And now I see I have 8 times the original definition of q of x. So reading the first line and the last line, doubling the input to q is the same as multiplying the output by 8. This is the pattern we saw in the table.